All right, so in this one, we're going to talk about applications of vectors, particularly displacement and velocity. So two important ideas here is, you can read all of this, I'm not going to read it all out. Two important ideas are the idea of a vector quantity versus a scalar quantity. Now, they're two different things. Now, importantly, a vector quantity has magnitude and direction, whereas a scalar quantity is just a number, it just has magnitude. So you've got some examples there. Vector quantities that have magnitude and direction are displacement, velocity, and force. So displacement, it's not just about how far you traveled, it's what direction you traveled in. Whereas with a scalar quantity, you can see that's the opposite. We're just talking about distance. That doesn't tell you what direction you traveled in, it just tells you how far. Time is just a number, speed is a number, mass. These are all just numbers. That's what we mean by a scalar quantity. All right. Now, again, I'm not reading through all of this, but if a person were to walk from A to B, but to do so they walked north and then they walked east, we could say that their displacement, which is a vector quantity, would be 4 root 2 northeast. So again, that's giving us a magnitude here and a direction here. So a vector quantity, magnitude, and direction. Jumping into an example here, we have a particle that's moving from point A, 2, 2, to point B, negative 1, 3. Now, you might get asked to find the scalar quantity. You might get asked, how far did this person travel, or this particle travel? But you might also get asked to find the vector quantity, that is, how far and in what direction. Now, in this case, it says express the displacement vector of the particle in component form. And you might be saying, well, component form doesn't tell me a direction, but it is a vector quantity. It is capable of telling you the direction, and it's capable of telling you the distance. All right, so let's draw it up. All right, so this is what it looks like. A particle's moving from point 2, 2 to point negative 1, 3. Now, you might be asking about these blue lines here. We're using position vectors to talk about the points. So this is position vector 2, 2. This is position vector negative 1, 3. Express the displacement vector of the particles. So express this vector here. Now, I can just eyeball that, and I can tell you that that looks like negative 3i plus j. But we should be able to come up with a better way to do that. So we're trying to find the vector AB. And to find that vector AB, we do AO, so the first letter O, plus O, the second letter B. In other words, we're using the reverse of the first vector, not OA, but AO, plus the second vector, or the second position vector, OB. So the reverse of OA is AO, which is going to be negative 2, or we can just do negative 2i plus 2j. And then we're adding our second vector here, which is negative 1 plus 3j. Just add these up. Now we've got negative 2i plus negative I is negative 3i. Negative 2j plus 3j is j. And that's the end of our question. You can see AB is in fact negative 3i plus j, so it's useful to draw a picture. But here's our mathematical way of, or our algebraic way of calculating it. Looking at velocity here. Now, importantly, velocity is not speed. Speed is just 80 kilometers per hour, 10 meters per second. Velocity, however, has a magnitude and a direction. So 80 kilometers an hour in the direction north. That is velocity because we're given a speed and the direction the speed's going in. 10 kilometers an hour on a bearing of 80 degrees, true. That is a velocity because it has a magnitude and a direction. 3i plus 4j meters per second. It's giving us a magnitude and a direction, that vector drawn in component form. Now, each of 80 kilometers and 10 kilometers, that's the speed the thing's going at. If you wanted to know the speed that 3i plus 4j meters per second was, you could just find the magnitude of that vector, which they've done there and found 5 meters per second. So nothing overly crazy there. Now later on, we'll look at a car that slows down and speeds up and stops, etc. For now, we're only looking at motion with constant velocity. That makes our life a lot easier. So the car is going at 80 kilometers an hour. It does not speed up. It does not slow down. Now, a formula for that, which you will be familiar with, you might not have seen it written this way, is S equals TV. Now, just to make sure we understand what all that means, equals times velocity. Now, don't ask me why S is displacement, but there we go. Displacement equals times velocity. You've seen that before. Speed equals distance over time. But this is slightly different this time because the displacement, remember, is a vector quantity. That's a vector. And the velocity as well is a vector quantity because they include magnitude and direction. Now, time is not a vector quantity. Time is a scalar. So this is some vector is equal to a number times a vector. And it's probably easiest if we just jump into an example here so you can see what it looks like. Now, a particle starts at the point A with position vector OA equals I plus 3j. All right, so that's our starting point for our object. The particle begins moving with a constant velocity of 2i plus 4j. Find the position vector of the particle after 5 seconds. All right, probably the best thing we can do is start by finding our displacement vector. Now, the displacement vector, we can just use our little formula here. Try again. All right, so S equals TV. That's going to give us our displacement vector. So S equals 5 seconds times the velocity. And the velocity is 2i plus 4j. All right, so that looks like 10i plus 20j. Now, that is a displacement vector. In other words, that's an arrow that looks kind of like that, 10i plus 20j. That's an arrow that's showing the path of this particle. So our last step here is just to find its starting position. Starts with position vector OA, and then add the starting position to the displacement vector, or add the displacement vector to the starting position. And we will find its position vector there. All right, so position vector equals starting position, I plus 3j, plus the displacement vector, 10i plus 20j, and we'll have 11i plus 23j. All right, that's pretty straightforward. The next bit, a little more complicated, not just after 5 seconds, but after t seconds. So I can do exactly the same steps, or I can sort of bundle it all into one. I can say that the position vector of this object is going to be equal to its starting position, I plus 3j, plus this formula here, S equals TV, or just TV, plus time in t seconds times the velocity vector, 2i plus 4j. So what do I get? I get I plus 3j plus 2ti plus 4tj. And now I can group these, I can factorize. So I can say I, 1 plus 2t, and j, 3 minus 4t. Okay, and now we have, what do we have? We have a position vector that we can substitute any value in for t to find the position of this particle at any given time. 10 minutes now. This video has probably been long enough. I will have to do a part 2 here. Stay tuned.